Okay, so 24 gigahertz to 24.25 gigahertz and 77 gigahertz to 81 gigahertz. Is that okay? So if you say on, you're using a band pass filter, what was your cutoff frequency? On?
2 pi f.
No, I mean, which one did you take? Because the idea is that there are two separate bands, 24 gigahertz to 24.25 gigahertz and 77 to 81 gigahertz.
24 gigahertz.
You know, the band pass filter looks like, let me open a band pass filter. Was it 3.2? 3.2. Okay, somebody is recording. Let me record it as well. Oh, already. Okay. Band pass, band pass, band pass, band pass. This is 3.2. 3.3 is it? Where is it? Oh, 3.1. Oh, chapter 4. Chapter 4, I'm sorry. So this is a band pass filter, right? So looks like if you are using this one, this means you're using maybe, and if you want to get the frequencies from 24 until 81, then probably you're talking about 24 gigahertz until 81 gigahertz, right? So this is 21 related to 21, and this is about 24 and 81. But this means you're taking other bands as well. Do you follow? Let's take one by one. Let's take, if I'm just taking this band, SRR, short range radar band. Okay, so your omega 1 should be related to 77 gigahertz and omega 2 should be related to 81 gigahertz, right? And then you convert them into like omega and omega. 27 times 2 pi into 10 to the power 6 is omega 1, and then similarly omega 2. So this is okay. If you use this particular passband filter, you're okay. But the problem is there are two bands, two separate bands. And this shows that you might have to get two band pass filters. One for the ISM, 24 to 24.25 gigahertz, and another one for, so if I just take this one, this is this one for 24 24 to 24.25, and another one for 77 to 81 gigahertz. All right, do you follow? Has anyone tried this using two band pass filters?
Me, sir.
You did twice. Okay, then that was my question, that you need to use two band pass filters. All right, and you were supposed to show me something like, where is it? Something like this, probably. Okay, so this is low pass and high pass. This is for a simple band pass filter, but since we will be needing two band pass filters for ISM and another one, so they will take two parallel of the band pass filter. So yes, you have the main like everything together, but then you use this one to get ISM, and you use another this one to get SRR. If you have done it this way, then it's correct. All right, is everybody following? The idea was to get two of the bands together. I think all of you got either ISM with the long range or ISM with short range or ultra wideband with short range. So there are two distinct bands. If it was supposed to be, suppose it was something like 76 to 81, like long range and short range together, then you can have 76 until 81, then you can have all together. But since they are all separate bands, you need two band pass filters for each band. This band separate and then this band separate. Then it's okay. Very good. All right. So if you don't mind, Ong, shall I open your quiz in front of everyone? You didn't submit it here. Okay, then I have to go somewhere else to check it. All right. So shall we proceed to the topic? Any question, anyone? Can I get a raise of hands if everybody understood the quiz? Okay. Anyone who has not understood the idea? Parin? Is Parin here? He always raise his voice. That's good. Lukman, do you follow? Right. I think we are almost everyone here. 25 of you. Sharif, Nabihan, do you follow? Sharif, Nabihan, and Mohiman. Do you follow, guys? Sharif, okay. Nabihan, come back to the desktop. Wherever you are. We won't say anything to you. All right. So let's move to the topic for today. Let me just turn this off. Just we don't need this, and we don't need this. We just go for chapter 5. All right, so let's move to chapter 5. So far, what we have seen in network analysis is we started off using phasors, which was kind of a preview of circuit theory. Then we started using Laplace. We use Laplace because it's a bit convenient to solve the circuits in frequency domain. Reasons being the solution of differential equation and convolution. Two things are there that are not easy in time domain, but in frequency domain is much easier. We saw that the solution of differential equations are very convenient, and the circuits with even with the initial conditions are easy to solve. All right. However, one thing that needs to be highlighted is although Laplace is good for the solution, it cannot take care of the entire time from minus infinity to infinity. If you remember, it was from 0 to infinity. The Laplace was from 0 to infinity. So in a case in which we are required to see the entire time length, then it's not easy. If you must have seen that some of the signals are like two-sided, both sides, they have both sides. So it's not possible to solve using Laplace because it starts from 0 to infinity. Okay, so for that there was another guy named Fourier. We say Fourier, not the last R is probably not very clear. So Fourier series, Fourier transform, and their application for circuit analysis probably will we'll be focusing more on Fourier series and Fourier transform application. We'll see more will be from Fourier transform. All right. So the things that we'll be considering are trigonometric Fourier series, and related to this is exponential Fourier series. So we do these things together along with symmetry considerations. Circuit applications and average power, we'll do it along with Fourier transform. So 1, 2, and 5 are today's focus. Right. So in terms of so this is part 2, the definition of Fourier transform and properties of Fourier transform. So we're talking about part 1 today. Before we go into Fourier transform or Fourier series, let's just see what are the why we go in this direction. Okay, we experience periodic signals everywhere around us, and especially in terms of power circuits, we have sine waves and like the alternating currents and all. Periodic signals are in control, electronics, power systems, communication systems, etc. So they are everywhere around us. Okay, so this is one thing that we need to remember. Secondly, yeah, these are the types of periodic waves, periodic signals: sinusoids, square wave, pulses, sawtooth, etc. Not all periodic signals are easy to analyze, although they are many periodic signals, but not all the periodic signals are easy to analyze. Especially, just take this the simplest case of a square wave. A square wave is like plus and minus, or like high or low, which is very common, although very common, and looks like it's very simple, but it has discontinuity, like on off. It's like a discontinuity. So this makes it not very easy to analyze. And then considering others, the sawtooth also not very easy. Okay. For analog systems, the solution is differential equations. So this is another thing to keep in mind, that the solution is differential equations. And if you remember from solution of differential equations, we were looking for those lambda values. It contains sine and cosines or exponential function. Okay, so the solutions may have sinusoidal components. So I'm narrowing my discussion towards sinusoids. And analog systems also have sinusoidal responses. So, all the analog systems, the capacitor, inductor, they have exponential, which can be expanded into sinusoids. So we are talking about sinusoids a lot. This means we need to focus more on sinusoidal signals, which is like the sine and cosine, are much easier to analyze due to their periodic properties. We know that after every 2 pi they are the same, and because of the converse of sine and cosine, when one is high, one is zero, the other is high, the other is zero, and so on. So we'll make use of those properties. The solution of differential equations are also kind of sinusoidal. If there's a way to represent, so as I mentioned in the previous one, not all periodic signals are easy to analyze, but if it is possible to represent any periodic signal in terms of sinusoids, it will be handy to use the properties that these sinusoids have, right? So yeah, the way is Fourier series. Fourier series is a way to represent any periodic signal in terms of sinusoid. It's like breaking down any periodic signal into smaller components of those sinusoids, and we'll have many of them. We need like not just one or two, we need many of them to compose that particular signal. It's like, in the number system, we have unit, tens, 100,000, and then 1/10 and 100 and 1,000th, all these. So we can break it down into smaller numbers to easily analyze them. So although it looks like a complicated process, but once it is broken down, we have those simpler components available to us. And once we have those components available to us, we can apply the properties very easily to analyze. Okay, you might think that this is going way too far to simplify it. Yes, indeed, it will be simplified once it is broken down into those components. So we are trying to see those components Once we have those components, we can apply different properties to solve them. All right. It's just like breaking down any problem into smaller components. And once we have those smaller components, we solve each of them separately and then combine them. This is kind of superposition principle also. Then when we have a circuit or system with multiple sources or multiple forcing functions, we break them down into individual, analyze them, and then solve them. We apply the same approach here. So the name is after John Baptist Joseph Fourier. He was in 17th and 18th century. Uh, he came up with the insight that in any practical periodic function can be represented as sum of sinusoids. You might think how we can convert a square wave into sinusoids. He proved it. Such a representation, along with the superposition theorem, allows us to find the response of circuits to arbitrary periodic inputs using phasor techniques. So once phasor, okay, so remember phasors are also sinusoids. So if we can break them down into sinusoids, we can use the concept of phasors as well. Yeah. So what is a Fourier series, or at the moment trigonometric Fourier series? All right. So far, any question? 5, 4, 3, 2, 1. I'm not getting the messages on the chat window somehow. I don't know why. All right. Okay. So it is a representation that resolves. Let me bring down the laser pointer. That resolves, that breaks them down. The ft, the actual periodic function, into a DC component, so a DC value, and AC components comprising an infinite series of harmonic sinusoids. Okay, starting to be uh, starting to get confusing. Okay, never mind. If it's periodic, it's definitely alternating. So it's alternating. If it's periodic, like alternating, it will have an average value. Remember, every periodic signal, every alternating signal has a DC value or the average. So this is the DC value. And infinite series. So we have infinite terms. Don't worry, we'll go to infinity. Series, we have done the sequences in series. Yes, a series. Harmonic. What is harmonic? Uh, where is harmonic? Okay, I'll show you in a while. So basically, any periodic signal, if it is ft, this means ft plus nt, which repeats after a period. So after every nth period, it repeats itself. All right, where n is an integer and t is a period of the function. So we are breaking this one into these two, which is a naught comes out to be the DC component, then a1, b1, a2, b2 into cos, sine, cos, sine, cos, sine. And you can see that the difference in each term is omega naught, 2 omega naught, 3 omega naught, and so on. Similarly, in the b1, sine omega naught, 2 omega naught, 3 omega naught, and so on. So harmonics are basically the multiples of the fundamental frequency. So infinite series of harmonic sinusoids means that this is the fundamental one. This is the fundamental frequency component. And then the harmonics of the fundamental. Harmonic means that the multiples of the fundamental frequency. So like 2 omega naught, then 3 omega naught, and so on. I need to see the messages. If you guys are messaging me, I don't know. Teams. I'm not able to see the messages. Where is team? Oh, really? Why is that? You mean my other device is in a different meeting room? Okay, let me join again. It's the same meeting room. I'm joining the same. Okay, now I can see the messages. All right, thank you. I got the first two. Can someone type another message? I won't type anything. Test message. Okay, got it. Thank you. Thank you. All right. Hmm. So I was talking about harmonic. So basically, one is the DC component, the average value. So this is the average value. Then this is the basic fundamental frequency component, and then these are the harmonics. Harmonics means that these are multiples of the fundamental frequency. All right. So this is the most important thing, but these are also multiple of harmonic components. All right, we'll get to know more as we go along, so don't worry. If anyone has a question, please don't hesitate to ask. Okay, as I go back, I lose all the messages, so I should not close the messages. Let me join again. I lost the messages again. Anyhow, please, if you have a message, please like unmute your mic and just ask me to read the message. Okay. Right. So, keeping in mind the actual expansion, so we have expanded or resolved the basic signal into a naught plus a1 cos omega naught t. It's like unit, tens, hundred, thousand, and so on. So don't worry. This is like just expanding into multiple frequency components. We can also write it like a naught is separate, and then from n1 to infinity, it's like a1 b1, it's like an and bn, and this one having cos n omega naught t, so it's like a1 cos omega naught t plus b1 sin omega naught t plus a2 cos 2 omega naught t plus b2 sin 2 omega naught t plus a3 cos 3 omega naught t plus b3 sin 3 omega naught t, and so on. Right, so this is like a closed form because we cannot keep on writing all these terms here. So this is the DC component and this is the AC component. All right. The sinusoid sine n omega naught t or cos n omega naught t is called the nth harmonic of f of t. So harmonic frequency, what are harmonic frequencies? It's like, first of all, it's the multiple of the fundamental frequency. Okay. And we sometimes see when when something is oscillating, with that oscillation, uh, some smaller components also oscillate with multiple of the basic frequency. You can say that. Okay, these components are normally smaller, and as you go like far from 1 to 2 and 3, they become smaller and smaller and smaller, and they decay. So the first 2 or 3 or maximum 5 components are the ones which are contributing to the main thing. Other things are very small. It is an odd harmonic if n is odd, and even harmonic if n is even. So it's like just defining them into, if like n1, 3, 5, 7, they are called odd harmonics, and for 2, 4, 6, 8 are called even harmonics. Okay, as I said, harmonic frequency omega n is an integral multiple of the fundamental frequency omega naught. So omega n is equal to n times omega naught. All right, any questions so far? This is just defining the terms, playing this the ground first, setting the field first. Okay, can I proceed? Oh, okay, this is just just like when we are talking about the existence. So there are some conditions to be met, which at least for this course we'll be keeping them true, that we need to know, and these conditions are called Dirichlet conditions. It's a single valued everywhere. So at any point in time, any point in t, for one t, it's like having just one value. It's not possible to have two values at the same time instant. Okay, so we are not considering the signals which may have two values at the same time instant. Okay, and it has finite number of finite discontinuities in any one period. It will have, it may have some discontinuities, discontinuities are basically, so if this is the signal, and if suppose this is going like this, if it suddenly changes, this is a discontinuity. Okay, this is a discontinuity, this is a discontinuity. Okay, so for during one period, it may have finite number of finite discontinuity, not infinite. It should not go like this to the like this is not possible. It should be like finite, so like going from one value to another value. Okay, and the value like this, but it cannot have say suppose infinite number, and it cannot go to infinity like this, right? Then it has finite number of maxima and minima in any one period. So maximum minimum should not be like infinite maxima and infinite minima. It may have different uh, like more than one maxima and minima. You know, maxima minima is, suppose if the function once again is like this. Okay, in this particular signal, how many maxima and minima? One maxima and one minima, right? But maybe if we draw it like this, so it has one maxima here, one maxima here, one minima here, one minima here, another minima here. So every time it changes the slope, every time it changes the slope from positive to negative, negative to positive, there is a minima or maxima there. Okay, so it may have finite number of those, but not infinite, right? Again, this is just a condition that we make need to have to in order to find the Fourier series. And finally, the integral, this integration, because eventually we are going to do the integration, this integral should be bounded. It should be like less, there should be like a number. It should not be like a very big number or like infinity. Remember, this infinity is a relative term. I think I'd mentioned before as well. Infinity is a relative term for something which is rated for 1 milliampere. If you give it 1 ampere, it will burn. A transistor will burn if it is rated for 1 milliampere and we give 1 ampere, it will burn. So for that transistor, 1 is infinity. But for an aircon which is rated for 16 amperes, 1 ampere or 2 ampere or like maybe 20 ampere, it might survive. But for the 16 ampere one, 100 ampere will be infinite. So that's a relative term. For theoretical purposes, we are talking about this one as the something upon zero or a very big number. But for physical systems, this is actually a number. There is a bound, so that integral should be within that bound, right? But theoretically, it should not be infinite. So if these four conditions are met, Fourier series exist. Okay, uh, convergent. Convergent means that okay, let me draw it again. Convergence means that if suppose this is suppose the boundary or something, or so it will be converging to this value. Okay, or something like this, or something like this, or some it converges. You see it's converging, but what is like divergent? Divergent is going like this. This is going infinity. So it may be possible to have a divergent series, but which will not have a Fourier series. If you remember from your sequences and series, sum of infinite numbers was something like s equal, today I don't have my pen, 1 upon, or maybe a upon 1 minus r. This is only true if r is less than 1. If you remember, this is from sequences and series, so this is something similar to that. Don't worry, this is just to highlight that these conditions should be met before we find the Fourier series. For our discussion, they will always be met. All right, so analysis. Analysis means like actually finding out and then eventually expressing the function f of t in terms of the Fourier series. So analysis means in order to have the function ft represented as sum of sinusoids, we need to find the Fourier coefficients a naught, a n, and b n. And the process of finding the a naught, a n, b n is called Fourier analysis. And actually, that's the main task. In order to express a function ft in Fourier series, we need to find a naught, a n, b n, and this is what where all the effort will be spent on. And for that, luckily, we have some good trigonometric relations available. So, alhamdulillah, that we have those mathematicians who uh, who made our life easy, but there were some more mathematicians who made our life miserable, like Fourier. So, okay. So before we go into the Fourier analysis, let's recall or remember some of the trigonometric relations. Uh, just to uh, highlight once again, integration over a period or integration is actually area under the curve, and it is also the average, taking the average value also. Okay, so if you remember, if you recall, any sine function if integrated over one period will be zero because the average is zero. So whatever it goes up, it comes down, will be zero. Similarly for cosine, which is something like this. So whatever the positive values will be cancelled out with the negative values, and the average is zero. So the average of sine or average of cosine over one period is zero. Okay, I hope you remember this. Okay, this is one. This is like two actually, not one. Then if it is sine and cosine multiplied will also result in zero over one period. Okay, so it's something like this. If they are like sine and cosine, so this is a sine and this is a cosine. If they're even multiplied, will eventually also have some of the positive values, some of the negative values. They will cancel each other. So this is also zero. All right. Then if it is sine and sine, is if it's a product of two sine wave with different frequencies, will also result in zero for all m not equal to n. So if it's suppose sine n, sine 2 and sine 3 omega naught, or like sine 5 or and sine 5 7 omega naught, if it's they're different, also zero, right? But if they are same, they will become sine square, right? If it's same, it will become sine square, and which results into a simple number t by 2. Again, just so far 0 0 0 0 and a very simple term t by 2. Similarly for cosine also will be 0 if m is not equal to n, and if they are same, it's also t by 2. Right? Any question? Why is it I'm concerned? Okay. All right. Else. Okay, yeah, wonderful. I was going through some of the videos that will make your life easy, at least for understanding. I have seen that this Han Academy videos are very nice. And let me just show you just one example, maybe. And they have shown the way I used to do with a pen and the board, and it will be very useful in understanding. Where is it? So it has all the different. So I would like you to go through all these videos. Please go through all the. It will take maybe 1 hour maximum, but it will explain to you like much better than me. I'm sure because they have done it step by step and everything. I'm using the results, but please go through all these videos in which you will. Let me just show you this one. So they're starting with this thing and explaining what's and whys of everything. So I'm sure that this will, and they have done it the same way that I used to do it, with a much better handwriting. I do it with a much better handwriting, really, right? No, they have done it much better, right? So please go through all these videos. Probably I'll take a quiz from these videos itself so that you guys follow, right? Okay. So once we have all these values available, we now move forward to find the values of a naught and an and bn. All right, it's not difficult, and again all this is also there in a much better way in those videos, but I'm doing it here just for the sake of completeness. But I would again request all of you to go through those videos. I'm gonna take a quiz from those. Okay, let's tomorrow we have a quiz from those videos so that you guys go through. Nothing else. Tomorrow just a quiz from those videos, all those videos. All right, so in order to evaluate a naught, let's integrate both sides. Okay, this is there are different ways to find values. Actually, this is an equation. Actually, we can do a lot of things, but one way to do it is to use integration. So we're integrating over one period. So this is like integrating. Okay, what's the benefit of this? We make use of the previous ones. Remember, integration can be applied to individual terms. So apply it to a naught, and then apply it to this summation as well. It will go inside. We can do that. And if you remember that the integration of the cos functions, individual and sine functions, because they are the average values, they will go to 0. So we just left with a naught dt, or when we do integration we get a naught t, right? So far so good. So we still didn't find a naught, by the way. We have to find a naught. So what is a naught? A naught is, we just take this t down here. So a naught is 1 upon t integration of the actual function dt. This is how we find a naught. So we are given a function, we just bring the function here, integrate it over one period, divide by t, we get a naught. And once again, if you want to go, you'll go to the Khan Academy videos to see the so the same thing is done with, like, by hand. So that gives you more understanding, but at the moment we will use this as a result. All right. When we talk about an, so we need to find an. An are the terms along cosine and omega naught t. Again, this is an equation, and we need to find an's which are infinite an's. So we cannot find the infinite terms from one equation. We need to find a way, and the way to do it, again, some mathematicians helped us. They did it in a way that multiply both sides by cos m omega naught t and integrate over one period. So we are multiplying cos m omega naught t here, m omega naught t here, m omega naught t here, m omega naught t here. So it looks like this: cos m omega naught t, and this expanding. So this comes here, along with this comes here, and this comes here, all this together. And if you, let me just go back to those, yeah, here. So if cos and cos are together, they will result in 0 unless this is here. And sine and cos, if there are two different ones, they will eventually be 0. So for our case, this will be 0 for sure, because there are two different terms, sine and cosine. And this will also be 0 unless n is equal to m, and this will also be 0. Okay, so integral containing a naught becomes 0 because it's just the average value. Good. Integral containing the sine terms will also be 0. The bn also be 0 because I just showed you. And this will also be 0 except when m is equal to n. So this is almost 0 except m is, so this will become cos square. So it will be like cos m or n, whatever it is, square, and the integration of that was t by 2. All right, so we will get something like this. This equal an times t by, this is like for a particular case of n. So we are talking about n equal to 1 until infinity and m any value. But since we are talking about m equal to n, so that's why m is equal to n here, and we got t by 2. So a n t by 2, we took the t by 2 on the other side, 2 by t, and we can find the. All right, is that clear? Anyone? Take a look at it and let me know. Oh, this guy is, poor guy is doing the job for us. Can I get a raise of hands if everybody is following? So this is the formula that we are going to use. So please let me know if you guys are following. Can I get a raise of hands from everyone? 18, 19, 20, 21, 22, 23, 20, 23. Still, is there anyone who is not following? Please unmute his mic and let me know. I can do this again with you. Anyone? Shall I proceed?
Yes, sir.
All right. Thank you, Tan. So once again, if you want to see the evaluation, you can go through those videos and do that. You can unraise your hand. Thank you very much. And similarly, this time around we multiply with cos. If you multiply with sine, there will be a sine here and a sine here, sine here, sine here, and sine here, and we'll get just the sine square term here, and which will result in 2 by t, t by 2, and eventually we get 2 by. So we have the a naught, we have the an, and we have the bn. We have the formula. How to find a naught? A naught, I think I've compiled somewhere. Yeah, a naught is 1 upon t integral 0 to t ft. So whatever function is given, put it in the integration, integrate from 0 to t and divide by 1 upon t. We get a naught. For a n, multiply with cos n omega naught t and then integrate and multiply with 2 upon t, and for bn, multiply with sine n omega naught t. If you remember, it is something similar to finding Laplace. Remember, instead of this cos n omega naught t, we were multiplying e to the minus st. So eventually we will see that this cos and sine will come together to make the exponential function. But at the moment, just focus on this one. And alternative form of ft could be, we combine them and write them in phasor form. We'll come to this in detail, but anyways, this could be one way to show it, combining an as an square plus bn square. If you remember, cos square and sine square will become, could be combined, and the tan inverse. So each of these an and bn can be combined into single an, and which will be an square plus bn square. So if suppose it's a2 and b2, so capital A2 is a2 square plus b2 square, comma phi 2 is tan inverse b2 upon a2. So we can also express them in phasors, and this will result in phasors an cos phi n, sorry, an and angle phi n. So this is one reason why we use cosine and sine functions to express them, uh, that can be used to express them in phasors. All right, so yeah, so this is how we get it. I think that the previous one should have come after I have discussed everything. We apply the trigonometric identity cos alpha plus beta is cos alpha cos beta minus sin alpha sin beta. So if we apply this here, it's like this is alpha and this is beta. So cos alpha cos beta. So cos this plus like cos this times cos this minus sin this minus sin this times sin this, like this, right? Okay, so this is cos alpha plus beta. So cos alpha cos beta minus sin alpha sin beta. And by comparison, if you compare, an is an cos phi n. Now we're comparing this with what? Please go there. I want this one. Let me bring it here somewhere. So by comparison, so we can see that an cos phi is actually an, and an sin phi is minus. Because I'm in a class. Can I come to you after the class, or maybe at in 5 minutes? I'll come in 5 minutes. 5 minutes. So once again, this was the actual expansion an cos n omega naught t. So cos n omega naught t is still there, and except this an is replaced by an cos phi. So this means an is equal to capital An cos phi n. Similarly, bn is replaced by minus capital An sin phi n, and yeah, right. So and also the angle is like phi n, bn upon an. All right. Any question? So far we have done just the definition, and we will use the definition to use Fourier transform in expressing any signal into these coefficients. All right. And when we want to plot an and phi n against the frequency, it will be the amplitude spectrum. Spectrum, by the way, is frequency, something against frequency. So on the x-axis is frequency, and the magnitude of phase is that's the spectrum, right? So the plot of an is amplitude spectrum, and plot of phi n is phase spectrum. And we combine them to get the frequency spectrum. Just again, just naming them. Okay, so since we have seen that we are integrating a function multiplied with sine and cosine, we may try to recall some of the functions and values from our calculus and other courses. They were supposed to come one by one, but anyways, remember the integration of cosine is sine, and if it is like a is 1 upon a, integration of sine is minus 1 upon a cosine at. If it's t times cosine at, we'll use integration by parts. So this will be the expansion. You can use this as your reference. Similarly, if t sine at, I don't think we'll go further than these functions, but this would be enough to find to give you the insight on the Fourier series. Similarly, cos 2 n pi is 1, sine 2 n pi is 0, and so on for different values. So this is just like the table thingy for Fourier series. All right. Once we have this, let's find the Fourier trigonometric Fourier series of this function. Let me just introduce this problem, and then we'll take a break for 5 to 10 minutes, and I'll go and sign this paper. All right. So we have this function ft, and we want to have the Fourier series expansion of this waveform. The things that we need is the function itself, and we need omega naught. So for that omega naught, we need this time period, which is 2. We can get omega naught from this because this is 2. So the frequency, the basic frequency is 1 upon 2. and we get omega equal 2 pi f or 2 pi by t, we can get omega naught. Some they were supposed to be like step by step, so don't worry, I'll just fix it. All right, so let me just we'll just take a break for okay, this time 10 minutes. You can go through the previous something if you want. Okay, which one should I stop at? Maybe I think this would be the best one. Yeah, take 5. 10, sorry. All right, welcome back. We have some carbon expression where m is not equal to n. I think you asked this question about this slide. Again, I'm not getting the messages. Mhm. Okay, you, Hang Chin Tian, how about the expressions when m is not equal to n? I think you're asking about, still don't have it. This one or something else? When m is not equal to n, then they will be 0. But when m is equal to n, this will become cos square. Okay, this is using, where is it? So you see that this is when m is not equal to n, this will be 0. This will be 0. But when m is equal to n, this will become sine square, this will become cosine square, and this is where it becomes t by 2 or t by 2. If that answers your question. Is that clear? So when we are looking at an, so you see that this will be 0 obviously. This is two different one, also 0. This will be 0 for all the m not equal to n, but only when m is equal to n, it will be equal to t by 2. I just showed you. And that's why this will be equal to an t by 2, and what? And we just bring t by 2 on the other side to get an value. Right? Similarly for bn also. But you can go through the videos, you can easily see all those. All right, we were doing this question. Okay, so what to do is, the first step is we describe the waveform in terms of some function, some value, some time, some t or a b c something. So we know that from 0 to 1 it's 1, and from 1 to 2 it's 0, which shows this. Between 0 and 1 is equal to 1, and between 1 to 2 it's equal to 0. What is the time period of this function? Time period is 2. That's why omega naught is equal to 2 pi by t, or just pi. So the fundamental frequency is pi, and then we will be looking at pi, 2 pi, 3 pi, 4 pi as the harmonic frequencies. So just how to find a naught, a n, and b n is a naught is 1 upon t, 0 to t, ft dt. What is ft? Ft is 1 and 0. So for 0 to 1, it will be 1. From 1 to 2, so we can split the limit from 0 to 1 and 1 to 2. See, 0 to 1 and 1 to 2. The value, this is 1 upon 2. So this one is very simple. And this is 0. The answer for this one will be t, and we will put 1 and 0, the limit. We'll get just 1 upon 2. Is that clear? From the beginning, we express the the function in these values, like, okay, what is the value between every changing limits? So it's 1 and 0. Between 0 and 1 is 1. Between 1 and 2 it's 0. Okay, we find the time period from the waveform. We find a naught using the formula 1 upon t integral 0 to t ft dt. Ft can be split into 2 because there are two different values for two different times. From 0 to 1, 1. You can see that 0 to 1 is 1, and from 1 to 2 is 0. So this will be 0. We integrate this, we get t, applying limit 1 to 0 to 1, we'll get just 1 upon 2, right? Similarly, an is this is the formula. We have to multiply cos n omega naught t, and when we integrate again, we can split it into two, from 0 to 1 and 1 to 2, just like that. From 0 to 1 and 1 to 2. From 0 to 1 is 1, from 1 to 2 is 0, so this will be just 0. There should be a bracket here. And when we integrate this cos n pi t, we remember it's like 1 upon n pi sine t will be the answer. 1 upon n pi sine n pi t. There should be a bracket somewhere. Oh, 2 by 2 is cancelled. There should be a bracket here. And when we apply the limit, we apply limit sine n pi minus sine 0. Sine of any pi is 0 and sine 0 is also 0. So we get a 0 for this function. Any question? Nazrul, I will of course post the slides on ulearn and the video as well. I didn't pause it in the middle. Or did somebody pause it? All right, find Bn is same as An, but we'll be having sine n omega naught t. So we have 2 by t ft sine n omega naught t. Same way we split it into 1 to 0 to 1 and 1 to 2. So 0 to 1 and 1 to 2, and this will be 0. Only this is left, and we get the function in terms of cosine with a negative. Remember, integral of sine is negative cosine. And when we apply limit, it's n pi by t and 0 pi by t. Cos 0 is 1 and cos n pi depending upon n, because if you remember from n pi, for even and odd pi, it's like negative and positive, negative and positive. So it's like this. Cos n pi is equal to minus 1 to the power. And this is also given in that table I just mentioned in the few slides back. So we can get, don't worry about this. This is just to how to write it. So don't worry. When of course we'll get 1, it will be 0. That's why for even n is 0, and for odd n it will be this negative and negative 2. So 2 n pi, 2 upon n pi. Is it okay? Once again, this minus goes inside. So it's like 1 minus minus 1 to the power n, because cos n pi is minus 1 to the power n. And just put the value of n odd. If it's odd, it will be negative, and this negative will become positive, will become 2 upon n pi. When n is even, this will become positive, and positive and negative become negative. 1 minus 1 is 0, and we get, this is how we get Bn. So we have a naught, we have an, we have Bn. We see this 1 upon 2 is the average of this this wave, and we can see that this is true also. The half of the time is 1 and the remaining time is 0, so between 1 and 0. That's why we get 1 upon 2 as the average value of. All right, so far so good. Can we have a raise of hands if all of those here are following? That's fast. Anyone not following, please don't hesitate. And I think this example is also there in that Khan Academy video as well. But this, I've tried to make it as easy as possible. All right, thank you, and raise your hands. Okay, and this is just to show in. So since an was under root an square plus bn square, so an is 0, so it's just bn, magnitude bn, and phi is bn upon an. So if an is 0 and bn is like also 0 and this value, that's why we got minus 90, because infinity. So yeah, and this is what we get. Okay, now this is interesting. So far so good, right? An was 1 upon 2. So an against omega, we have like broken down our function in frequency domain. So at a0 you get 0.5, right? And then we have these harmonic frequencies. At pi we get 2 upon pi. So this is if n is equal to 1, so this means pi, so this is the value of 2 upon pi. For 2 we will be getting these at yeah how we got these values. These values are coming from harmonic frequencies, and each one of them is appearing at that particular harmonic. So that's why it's like odd, even, odd, even, odd, even. We can see, I should have explained it first. Okay, this x-axis is the omega, and it will have the harmonic frequencies. This is the fundamental frequency, then first harmonic, second harmonic, third harmonic, and so on. For even numbers of harmonics, like 2 are the values of an, and for odd will be the value of bn. So this pi and 3 pi and 5 pi are bn. So we just put n equal to 1, we get 2 upon pi. So the amplitude is 2 upon pi. At, of course, 2, if it's 2, it will be 0 because it's actually an, which is 0. Similarly, at 3 will be 2 upon 3 pi and 2 upon 5, and this will be like going down like this, decaying. All right, is okay. And similarly, we got for n equal to odd is minus 90, for n equals 0. So at like first harmonic frequency and then so on, we get the angles. So this is amplitude and phase spectrum. All right. So what do we get? What was our initial goal? Our initial goal was to, this was not supposed to be here. So what do we get actually? We were supposed to get this one representing, what is this representing, by the way? If I ask you, what is this representing? Can anyone say what is this function representing? Can anyone tell me what is this representing? What is this Fourier series representing? Anyone? Has anyone typed something? Am I online or not? Yeah, I'm online. So basically, this was supposed to represent this signal, right? The question was to determine the Fourier series of the waveform shown below, obtain the this is the function, this is the waveform, and we were supposed to get something that represents this. And what we get at the end is some strange numbers like this. Hmm? Where did this sign come from? Okay, until this far we only found a naught, an and bn's. A naught is 1 upon 2, an is all the an's are 0 and bn's are these values, right? So this is not Fourier series, these are Fourier series coefficients. Okay, so after once we have found all the coefficients, we actually place them in this expansion. Okay, it's supposed to be a bit lower. Do you follow? So we have the a naughts and a n's and b n's. A n are all 0, b n are like alternating, so 1, 3, 5 and so on. Okay, so we place this one along with this. Don't miss out to express the final function in terms of the Fourier series coefficients and all. This is the final Fourier series expansion. Okay, this is important. Uh, uh, Normally we will be very happy to find a naught, a n, b n, done, answer finished. Next question. No, it's not like that. We have found the coefficients right now. We have not found the Fourier series expansion. Fourier series expansion is this. So we place all those numbers here. A naught is 1 upon 2. So you can see 1 upon 2. A1 is 0. Okay. A2 is 0, A3. So all the cosine functions are gone. This is all 0. Even this one, only odd numbers are there. So B1, B3, B5. That's why I said 2 upon pi, 2 upon 3 pi, 2 upon 5. So this is coming from this or this 2 upon n pi, odd only. Evens, even they are 0. Right? So we put all the terms here to get this expansion. Still, is it a square wave? We expected that yeah, this is a closed form. This is just a closed form. If you don't have enough time to close it, just leave it like this, or if you can, this is just representing an odd number. 2k minus 1 is an odd number. So this is the way. So 2 upon pi is common. 1 upon 1, 1 upon 3, 1 upon 5 is 1 upon n, with only k are only odd numbers. So n are only odd numbers. So we get this as a closed form. We expected that the Fourier series will be able to represent any signal ft. It was supposed to represent a square wave. Is this by any means a square wave? At least visibly not. It's a sine wave or sum of different sines. Okay, this was intended that a function can be expressed in a sum of sinusoids. So at least we have done what we have done is a sum of different sinusoids. But is it a square wave? Let's see. So once again, this was the original function, and this is the expansion. Now we want to see are they representing a square wave? Okay, let's just take the first term only. First term is a DC component, AC, so just 1 upon 2. All right. Second component is a simple sine wave, which has the fundamental AC component. By the way, if you just add these two, this will be shifted up. So this will be at this point and this will be at 1. So at least we can say that this square wave is now converted into a sine wave with an average of 0.5. Are you following? Are you following, guys? I hope you are following.
Yes, sir.
Okay, wonderful. Thank you. So this is just one. Okay, how about this one? This one is this one together with this is something like this. So sum of first two AC components. So the sum of these two is this. Sum of these three is this. And if you take fourth term, like also fourth term is something like this. And I think now you can see that where it's going. So the more terms you have, you're becoming closer to a square wave, something like a square wave. And if we actually go to infinite terms, it will be something like this, right? So this is when we go to 11th, n equal to 11. It's like very close to a square wave and so on. All right. So once again, this was the expansion of this one, which didn't look like a square wave, but this was promised that we can express a signal in terms of sinusoids. So this is sinusoids, and when we combine all these, when we keep on combining the terms, we will get closer and closer and closer and closer to the actual square wave. Okay. Now one would ask, um, this was my function. This was my function 1 0, and we made it look like very complicated, something like this one. Yes. Why is it? Is someone needing control? I don't think so. Any comment? No, nothing. Okay. So this basically breaks it down into smaller and smaller and simpler components, which by analysis, it's much easier to do the analysis rather than those actual ones and zeros. Uh, it makes it looks a bit difficult to understand it, but when we do actual analysis, these are much easier and much easier to. One more important thing is all the analog circuits, the response is sinusoid, so we can have different analog components to actually implement these in actual life, and this is why Fourier series is very handy. Right. So let's move to. Okay, so this is an example that we can do. So it's like instead of 1 and 0, we have 1 and -1. So it's a very similar one, and I expect that you guys can do it by just placing. So instead of placing a 0 here, we'll have a -1. Similarly, for this one, we'll have a yeah like -1 here and -1 here. We'll get a new value, but still the same process. We won't be going into many like very complicated signals. Maximum like a ramp, sawtooth. Right. So now let's find some more shortcuts. One of the shortcuts are using symmetry considerations. Okay, what's symmetry? Maybe you have seen this in your signal system. And even symmetry is a function, or a function with even symmetry is that if we flip it across the x-axis or across the origin y-axis, we'll have a mirror image. So if you like to see that whatever is here is here, we have a mirror image on the left and right side of the y-axis. So if f of t is a function, it will be equal to if the t is reversed. So if t by 2 value is -a, minus t by 2 is also -a. At t the value is a, at minus t the value is also a. So we just change the time variables sign, we get the same value. This means it's an even symmetry. And these are a few examples like sawtooth or pulse or something like this. These are so just print it on a paper and fold it from this line, fold it like this. It will be like copying to each other. And if there is even symmetry, of course, there will be odd symmetry as well. Then this is okay. The property for even symmetry, even functions. Good thing is that we don't need to. I think I should have mentioned when we do the integration and finding a n and b n. Instead of going from 0 to t, we can also go from the t by 2 to t by 2. For this one, we went from 0 to 2. We could have also gone from 1 to 3, or minus 2 to 0, or minus 1 to 1. So whatever the time is, they divide by 2, and we can go minus 1 to 1 also. It is also possible. And this, in fact, we'll be doing it for some, like many of the cases. All right. So we just whenever we have an even function, and if it's like minus t by 2 to t by 2, and we know that from 0 to t by 2, it will be equal to minus 2 by 2 to 0. We have seen this in here. So 0 to t by 2 and minus like 0 to minus t by 2 are the same. This means we don't need to do it for the entire time period. If we just do it from 0 to t by 2, we are actually finding this function as well. So we don't need to integrate for the whole period, but the half period is enough, and we just multiply by 2. So instead of integrating for the whole period, we just integrate for half of it, okay, and multiply by 2. This is one thing that we can make use of. Instead of integrating twice, we just integrate for the half. And this shows that for an even function, the good thing is, the best part is, bn is 0, and a naught is 2 by t. The difference here is just 0 to t, is like just 0 to t by 2, and an is also 4 upon 2, 4 upon t, 0 to t by 2. So we're just doing it for half period. For half period, I'm multiplying by 2. Half period multiplying by 2. Right? You can derive these equations. I would encourage you to do that. Yep. All right. So for even functions, bn is 0. Very good. A naught is like finding a naught. You don't need to integrate for the whole period. Just integrate for the half period. Multiply by 2. Integrate for half the period. Multiply by 2. For odd symmetry, it's when we do the time reversal, we also reverse the amplitude as well. So from 0 to whatever, let's say t by 2, when we reverse it, when we go to this side, the value is also negative, which was not the case in even symmetry. Even symmetry, we go from 0 to t by 2. It's like this. So it's like this. So if suppose at this value is at t by 2, it was minus a. At minus t by 2 is also minus a. But for odd, at, for example, maybe this is t by 4, maybe at t by 4 it's a, at minus t by 4 it's minus a. All right, you can see this one is better one. So at the time between 0 to t, it's 1, or like a. From 0 to minus t, it's minus 1. This t is actually should be here. This t is actually here. And this is much easier to understand. It's like odd symmetry. So for odd symmetry, let me draw it. To check if it is odd, just take one period and slash it like this, and then fold it. Fold it like this, and fold it like this. So like fold, if you look at my hand, fold it like this. Previous one was folding it like this. Now this one is folding it like this, if you can see my hand. All right. Something like that. Just to understand, make you understand, but like not exactly. This is how it looks like. So good thing about this, that both a naught and an are 0. Even better. Both a naught and an are 0. This time around we cannot, and this is another property of this, that between this and this is 0. Why is that? Because it's like average. we're taking the average, so average of this will be 0. That's why it's 0. And a naught, that's why, so you can see a naught is 0, which is the average. It's also 0. Not only a naught, but a n is also 0. We just need to find bn, again 4 upon t, and we just keep it like that. And half the period. Okay. So this one is Fourier series expansion for ft. I'm not doing it in detail, but we know that for this a naught is 0 and a n is 0. We just need to find b n only. Not very good, not very neat, but you can see that a naught and a n are 0. The period is 4. We found omega naught as like pi by 2. Bn is 4 upon t between 0 and t by 2 only, and we just put this. And again we split the limit because it's only 1 between 0 and 1, and after that it's 0. Okay, the period is 4, by the way. The period is 4, but we just need to do it from 0, actually 0 to 2, actually I'm sorry, 0 to 2. So t by 2 is 0 to 2. So we split between 0 and 1 and 1 to 2 because the values are different, 1 and 0. And we just integrate and find the values. Okay, so the main thing is to find bn in this one, and ft, we put bn inside the Fourier expansion. So don't worry, this is the same thing coming with bn, and this is the fundamental part of the Fourier expansion. This is sine component. So this all is bn. All right, and this is the sine component. This is the Fourier series expansion. How much time do we have? Oh my god. Shall we do it? Shall we not do it? 3 or 4 slides. Okay. Okay, a compact way to express Fourier series is expressed in exponential form, and this is coming from the basic Euler's identity. If you remember, 1 upon 2 e to the j theta plus e to the minus j theta, or 1 upon 2j e to the j theta minus e to the minus j theta are cosine and sine. So I can express the cosine and sine in the there's something is missing. Okay, basically just gathering the terms an and bn, like this is the sine and cosine, gathering the terms we can express it like that. I should have put more details. So this one is basically the cosine n omega naught t, and this is sine n omega naught t. Gathering the terms, we can express it like this. I should have like put more details, but since this is just the derivation, so we need to find the new coefficients. The good thing is we don't need to find 3, but just 1, Cn only. So we just need to find Cn, and Cn is basically, you can see that this is, if this is Cn or this is Cn, the other one is the conjugate. So C naught is again the same A naught, and Cn is An minus JBn upon 2, and the other one is, if this is An minus JBn, this is the complex conjugate. So Cn, the other one is the conjugate. So we just need to find Cn only to get the other one also, just change the sign. So this is one way to find it, that first we find A naught and A and Bn, and then find Cn and all this. Okay, this is one way, but we'll not use this one. But eventually the ft becomes C naught and Cn and C minus n. This is the exponential Fourier series, or in a closed form it's like this. Okay, this is the exponential Fourier series representation of any function ft. But we will not find the Cn using this formula. Rather, we'll use the other one, which is like similar to Laplace. Okay, so we can also find Cn using An and Bn, which was shown in the previous slide. But we will not use this. We can use it, but this is like extra work. But we can simplify our work by just finding using this one. So just one, and we get all of these. Right? So it's like placing e to the minus j and omega naught t to place in to find the Cn. Okay, I'll come to that this one. Okay, let's take the example first. I think this is the best way to do it. Find the exponential for a series of periodic function ft e to the power t between 0 and 2p. 2p is the period. So this means after every 2p the function is repeated. Okay, so it's a periodic. So one thing to remember, that we find the Fourier series of a periodic function. This is the first thing that we start with. Okay, the time, I think it's pi. It's not not 2p, it's pi. So this is like pi. Please fix it. Time is 2 pi. Omega naught is 2 pi by t and equal to 1. Hence, we are finding the Cn only. No need to find a n and b n separately. We can just put this one here. So the function is e to the power t. E to the power t is between 0 to 2 pi, because the period is 2 pi, and 1 upon 2 pi e to the t, e to the minus j n t. Omega naught is 1, so minus j n t, right? Okay, if we integrate, we this is like 1 minus j. We When we like multiply, we can take this common. So 1 minus j n t, 1 minus j n is common. When we integrate, we have 1 minus j n in the denominator with the limit 2 pi and 0. Okay, when we put the limit, we get 2 pi, and when we get 2 when we place 2 pi, it's like this, e to the e to the j 2 pi, and when we put 0, we get a 1, right? If it's too fast, because I'm like maybe rushing, but don't worry, we will uh, we can discuss this example again, but this is just applying limits. So we get, using Euler's identity, e to the minus j 2 pi n is cos 2 pi n minus j sine 2 pi n. We can expand it and we can get the values 1. So e to the minus j 2 pi n is also equal to 1. So we just have e to the 2 pi minus 1. So where is it? Yeah, this one. So this one is equal to this, and we just get, how did we get 85? Is e to the power 2 pi. This is a constant. Now there's no t here, by the way. So we can evaluate this number as 85 upon 1 minus jn. And we just keep on changing n, and we put them in exponential or complex. It's also called complex for a series, which was the Cn, which is Cn here. This is Cn, and e to the j omega jn omega naught t. Omega naught is 1. We multiply, we get this Fourier series expansion. So this one, for many of the students, this is the easier one to find out, because we just find one coefficient and we just place it. But if you feel comfortable, you can do the trigonometric Fourier series as well. But they both will have the same result. Magnitude and angle, and when you plot it, we get something like this. Okay, this is the example that we will do tomorrow. So tomorrow I'm gonna take a quiz on the videos that I just shared in the beginning, which is like expanding all those coefficients. We'll do some problems from Fourier series. I think we'll do some from the filter design as well, just to bring things more into perspective, inshallah. Any question? This is already too much today, but any question? Anyone? Can I get a raise of hands if all is clear? And I again request Jocelyn to please make the survey, please. Let's see if all are following. How many of you are here? 27 of you are here, but Few of you still. Sharif, Nabihan, Arif, Kanye, Tan. If you're not following, please share your problem. Don't hesitate. Okay. Jocelyn has shared the survey again. Please feel free to express your. All right. I hope that you have also marked your attendances. Please mark your attendance, and then you're free to go. Thank you very much. Tomorrow we'll have a short quiz, maybe a Kahoot type quiz if you like it, and we'll have tutorial, some of the questions that will help us to understand more. Okay, if you guys are done, thank you very much. I'm stopping the recording. I'll post the recording